Okay, so here is a curve, okay, in three-dimensional space. And the question is, what length is this curve? Okay, and that's not a trivial question to answer. Okay, here we have the luxury of being able to deform this string or wire so that it becomes a straight line, and now it's easy to measure its length. Okay, but let's assume the general case that we can't do that, and we have some complicated curve with twists and turns. And the question is, what is the length of the curve? That's what we're going to look at how to calculate now. Okay, and it turns out that any curve in 3D can be uniquely defined in terms of a few quantities. One is the length of it, the others are the curvature and torsion, and they tell you how the curve twists and turns through space. Okay, and we'll look at those after. Okay, but first let's look at the length of the curve. Okay, so let's think about a curve. Here is a curve, and it goes between 2 points A and B. And the question is, what is the length of the curve between A and B? Okay, so we can think of it intuitively first. Let's split up this curve into different little segments or sections. Okay, and let's call the length of each section delta S. Okay, and if your segments are small enough, then this delta S, for this delta S, the line or the curve will just look like a straight line in this vicinity. Okay, so the length here is delta S. And you can get this by just going delta X across and delta Y up. Okay, so the length of your section or segment, whatever, ds is just given by Pythagoras as delta x squared plus delta y squared, all square rooted. Okay, and then you can ask what the total length of the curve is. Let's call it L. The total length of the curve between A and B is going to be a sum of all of these delta s's. Okay, and when we take the sum, we take the limit that delta x goes to 0, i.e. that you have kind of an infinite number of segments. Okay, and this just becomes then an integral ds. Okay, along the curve between points A and B. Okay, so that's a bit of a hand-wavy, intuitive way to look at things. We can make it a bit more formal. So let's think about a curve. So here's a curve, or here's a section of a curve. And let's think about at time t. At time t, the curve, the point on the curve is r of t. Okay. So let's have an origin here, O. There's a vector, r of t, that takes us to a point on the curve at time t, or parameter t. And as this parameter t changes, then the curve is mapped out by the end point of this vector. Okay, so let's think about a later time, t plus some small increment in time, dt. And now the curve goes to r of t plus dt. Okay, so we're still on the curve, but we're at a different point on the curve. R of t plus dt. Okay, and we want to think about what the change in this vector r is in this time, small time dt. And the change is just this length here, this vector here, and we call that dr. Okay, so what we're saying is that dr is equal to r of t plus dt minus r of t. Okay, so all we've done is we've drawn two vectors and we've subtracted them. Okay, so to get from this point to this point, we go minus this plus this, and that's what we've done. Okay, so now we can define the element of length. Okay, and it's defined as the magnitude of this dr. Okay, this is the element of length. Okay, and if we have the curve parameterized in terms of t, then we can write this as dr by dt, dt. Okay, where it's always assumed that dt is greater than 0. Okay, so we're thinking about the parameter increasing. Okay, so we can bring it into the magnitude. Okay. All right, so we can write this in shorthand. So the derivative dr by dt we can write as r prime of t. Or if you think of t as the time, then dr by dt is the derivative of the coordinate with respect to time. That's just the velocity. Okay, so you've just done some mechanics, so hopefully this makes sense to you. So you can write this as the magnitude of the velocity vector, dt. Okay, and now when you're parameterizing a curve, t won't always be time as such, but it intuitively helps to think that changing the parameter means changing time. Okay, so ds equals the derivative, the magnitude of the derivative of the vector r at t, dt. Okay, and this is in practice what we'll use to calculate the lengths of curves. So if we have this, then the total length of the curve, L, between 2 points A and B, will be the integral between A and B of ds. Okay, so again we're going back to this image of just adding up all the little ds's. We now know what ds is in terms of our parameter t. Okay, it's the derivative of r with respect to t. We call that r prime. Okay, and going from A to B, okay, the total length of our curve. At point A, we have t being whatever the value of t is that takes us to point A. Okay, and at point B, t corresponds to whatever the value of t that takes us to point B. Okay, so these are two important formulae that you should burn into your mind. Okay, and in practice, we want to think about how we actually use these formulae to calculate lengths of curves of interest. Okay, so we're going to look at some examples. But first we can say typically what this ds actually is. Okay, so let me take this away. Okay, so let's think about a case in which the curve, so all the points on the curve are parameterized by some parameter t, and all the points on the curve are defined by r of t, and this equals x of t I, unit vector, plus y of t j, unit vector, plus z of t k, unit vector. Okay, so that's, let's be lazy and write it as shorthand. So this is x of t, y of t, and z of t. Okay, now we want if we want to calculate the length, we need this ds, this line element, or the element of length. So we see that we need not just to calculate the derivative of r, but also its magnitude. Okay, so we've got r. We now need to find its derivative and then its magnitude. So let's first find its derivative. So r prime, so dr by dt. Okay, dr by dt equals, it's d by dt of this vector x of t, y of t, z of t. Okay, I'm just still on the board, fine. And this equals just dx by dt, dy by dt, dz by dt. Okay, and it's a vector with these three components. Okay, so we found the derivative, but now we need to find the magnitude. And we know how to find the magnitude of a vector. It's just the square of all the components added, okay, with the square root in front. So the magnitude of this r is dx by dt all squared plus dy by dt all squared plus dz by dt all squared, and then all under the square root. Okay, so in practice, we can also write as this thing, dt. Okay, so let's just write it out. Dx by dt all squared plus dy by dt all squared plus dz by dt all squared, square root, and then dt, which is not in the square root. Okay, and so these are the working formula that will help us actually calculate lengths of curves. Okay, so one thing I didn't say, which is actually helpful to remember things, is that you see that ds equals the modulus of the velocity vector, so that's the speed, times the time. Okay, so ds equals the modulus of the velocity vector times the time. Okay, so this is distance equals speed times time. Okay, so this ds, it really is a length. Okay, if you're traveling with some speed, 1 meters per second, and you let 1 second pass, then you will travel 1 meter. Okay, so this s really is the length of the curve. Okay, and this is why it's called the element of length. Okay, so let's look at an example now. Okay, so to summarize what we just found, we have this element of length, which we call ds, and it's equal to, so this is distance, it's equal to the magnitude of the derivative of the coordinate. Okay, so if t is time, this is a velocity, and it's the magnitude, so it's the speed, times some dt, which may be time. Okay, so you can think of this as distance equals speed times time. Okay, and once we know the little line element, we can calculate the total length of a curve between 2 points A and B as the integral of ds between those 2 points. Okay, and we know what ds is, so this is just the integral of r prime of t magnitude dt between ta and tb. Okay, so ta is the value of t at which you're at point A, and tb is the value at t where you're at point B of the curve. Okay, so here's our curve, point A and B. Okay, so at TA you're here, at TB you're here. Okay, so it's all a little bit abstract. So let's think about an example. And let's go back to our DNA helix in 3-dimensional space. So we have x, we have y, and we have z. Okay, and there are, okay, so in general, yes, we have a vector r of t, parametrized by t, is x of t, y of t, z of t. Okay, so here our helix was like this. Okay, it had radius a, and it had a pitch defined by b. So we knew what x, y, and z were, is what I'm saying. So we knew what x of t is. It's a, the radius, a cosine t. Okay. Y of t is a sine t. And z of t is equal to bt. Okay. So we know what x, y, and z are. So we've got x, y, and z. And what we want to find, if we want to find the length of the curve, is the derivative of r. Okay, and the derivative of r is just dr by dt. So we get a prime on each of these. Okay, this is dr by dt, this is dx by dt, dy by dt, and dz by dt. And we know what these derivatives are. So x prime is dx by dt, so it's minus a sine t. Okay, y prime is the derivative of y by dt, and it's a cosine t. And the derivative of z by dt is z prime, and it's just b. Okay. So we found the derivative, that's this thing that we need, the r prime. And now we need to find its magnitude. Okay, so we found that r prime of t is equal to minus a sine t, a cosine t, b. Okay, and the magnitude of r prime t is just this squared plus this squared plus this squared. Okay, so we've got now with the square root, so square root of minus a sine t squared, so that's a squared sine squared t, plus this thing squared, dy by dt squared, so it's a squared cos squared t, plus b squared. That's the magnitude of our vector r prime. Okay, and you see that you can simplify this by bringing out an a squared sine squared t plus cosine squared t plus b squared. Okay, and what's sine squared plus cosine squared? Okay, yeah, it's just 1. So this is root a squared plus b squared. Okay, and that's the magnitude of this r prime of t. Okay, so for this helix, the length is just given by the magnitude of r prime of t, which we've just calculated to be the square root of a squared plus b squared, dt, between two limits, which we need to think about, ta and tb. Okay, so the question is, what's the length of one turn of this helix? So if we start here and we go one turn around, what is the length of that curve? Okay, so we need to think about what ta and tb are. Okay, so if we look at the parametrization of the helix, then when t equals 0, that's this point. Okay, and if you look down from z, you see as t increases, you see a circle formed. Okay, and one run or one turn of the helix takes us from t equals 0 right round to t equals 2 pi. Okay, so t is the angle. Okay, so we start we start at point A and we go to point B, and point A has t equals 0, and we end at point B, which has t equals 2 pi. Okay, we go round the circle once. Okay, so TA is 0, and TB is 2 pi. Okay, so a squared and b squared, they're just constants, so we can bring this whole thing in front of the integral. So this is just equal to the square root of a squared plus b squared integral dt from 0 to 2 pi. Okay, which is just 2 pi square root a squared plus b squared. So this is the length of one turn of our helix. Okay, so hopefully you can see that in practice it doesn't take a lot of work. Okay, you just write down that distance is speed times time, effectively. Okay, and you calculate the total length by doing the integral. Okay, so all you need to do is work out what the derivative of this coordinate r is, this vector r, and then take its magnitude, as we've just done. Okay, so hopefully that's useful, and there's other problems in the problem set that are related, that are calculating the lengths of other curves.